Thank you very much. Thank you for the introduction, and also, yeah, thank you for inviting me to this beautiful place. So yeah, the talk is going to be today. The talk is going to be about the code-based primitives, and yeah, I would like to start maybe with just like plan for the talk. I would start with preliminaries. Some of these things you have already seen in the last 2 days, but this is more used like to set up like the full set of things that you need to understand this talk, and also to establish notation. So this is going to be very light part. The second part is going to be about the coding problems. So we are moving from like coding theory now to the more like computer science area, where we discuss the computational hardness of the problems. And after that, I'm going to focus on code-based primitives, and in particular, 2 code-based primitives that are interesting from different points of view. But like one of the reasons why I decided to mention them is that because they're going through the standardization process, so they're quite well documented. And yeah, I will use them as examples of like relevant code-based primitives. So HQC is an example of the public key encryption and key encapsulation. And cross is an example of digital signatures. And yeah, in advance, I want to thank all the speakers of the previous days, because they introduced a lot of relevant definitions. So I will not need to do that myself. But I might actually ask you to help me with the definitions to be sure that we are on the same page. And also like this part, so HQC and cross, it's going to be slightly more technical. And in order to make it somehow interesting for you, but also for me, please do ask questions. So this part, like when you have like a lot of very like technical stuff, is going to be very hard to follow if we don't interact. So yeah, I will definitely ask questions to you, but yeah, please also feel free also to interrupt me when there is something unclear. Okay. Yeah, so let's start. So we are in the coding theory setting, where so the goal of like the coding theory is actually to enable one side, that is, we call the sender of a message. In this case, it's like some Alice that uses some digital device and wants to send a message to the receiver, which also has some digital device. And Alice comes up with some message that you can like imagine as a string of bits, or you can, so this, in our case, we will observe that as something that is like of fixed length. In general, it can be something that is like, really a stream that you can observe like in any everyday communication, digital communication. And in that case, you can just like observe parts of it as blocks. But for us, we will observe that as something of a fixed length. So Alice, or a sender, comes up with a message, and she wants to send it to Bob. And during this like sending, so we assume that there is a channel that is going to introduce some kind of noise. And in this setting, so the coding theory setting, so this noise comes from the environment. So it's something that like is happening due to the imperfection of the channel, rather than due to some like malicious behaviors of like someone outside. So we are still not in a crypto setting, so everyone is behaving nicely, but the errors still happen. And in that case, so once Alice sends the message, some errors will be added to the original message, and Bob will receive something that he might not be able to understand on the other side. And it might differ from the thing that Alice sent before. And one way to fight that and enable like correcting this type of problems, this type of errors, would be to add, for example, 1 bit like at the end of the message that you might have known as parity bit. And so in that case, what you can do, if you have like a message that is basically a string of bits, you can just like sum them up and add the parity bit at the end. So you know that if this parity bit has changed, the error has happened. But if it has not changed, we can say that we assume that the error like might have not happened, but maybe there was multiple errors that actually in the end caused to, that they are canceled at the end. So you can see that this type of like error correction or like this type of protection is not very efficient. So today we will try to talk about slightly more sophisticated methods than this, like adding a parity check bit at the end. And in particular, we will call that encoding. So through this process, like we take as a message, we take some like function that I denote by enc, and we provide something that we will call a code word. So it's basically encoding of your original message. We send this code word. We assume, again, that the errors will happen in the channel and that we will obtain some noisy code words on the receiver side. And the task is then to actually decode this message or equivalently to correct the errors. So our goal in the coding theory is to recover the original code word C, and from there the original message M. And in the very simple cases, so this encoding is done the way so that you at the beginning you have a message, at the end you have this additional redundancy that helps you correct the errors. So you also have some different type of systems, but the intuition is always the same. You're trying to recover the original message. And one thing to say here before I move to the non-so coding theory related stuff is that so in this system, what we want to achieve is actually that this encoding, decoding is very efficient, and it's very easy to perform this decoding on the receiver side. In the cryptographic setting, we will not have exactly the same goal, but I'm going to talk about that a bit later on. Okay, so far so good. The setting is clear. Okay. And now we go to the linear codes, to the topic of linear codes, which is basically a tool that enables us to perform this encoding and decoding, or actually objects that enables us to perform encoding and decoding. And I will start with slightly more mathematical interpretation of the process that I have just described. So again, we have a message that, as I mentioned, can be, is a kind of a bit stream of length k in this case. And we know that the symbols in this message can also be and they are not necessarily bits. They can also be some integer values, for example. And in that case, what we have is basically a message that is a point in the vector space fq to the k. So if the symbols are coming from the alphabet of size q, we are having a vector in the space fq to the k. And we can also observe the code word C that is now of length n as another vector point. And we will, in our case, we will take that in both for the original message and the encoded messages, we also have the same alphabet, so of size q. This will not change. What changes is actually the size of this vector space. So now the code word is in a larger vector space, fq to the n. And the way that we can obtain this code word from this smaller vector space to this larger vector space is using encoding algorithm. And you can see that basically as a linear map. So that's very simple part. And one thing that you have all already seen probably if you ever heard about coding theory is that the common way to perform this encoding is using a generator matrix that basically describes your code. So in that case, encoding is very simple. So you basically multiply your message with the generator matrix that is basically a matrix of size k times n with entries from alphabet of size q. And yeah, this operation of encoding in that case is very easy and efficient. So it can be done in polynomial time easily. Okay. And what we obtain this way is the set of all the possible code words that are actually obtained from the messages through this vector matrix multiplication. Oh, does work. Okay. So we will code. So what we call the linear code is basically a set of all code words that are obtained through this vector matrix multiplication, so message times the generator matrix, where the messages are coming from this space fq to the k. Okay? And what you can also see from there is that basically C is a linear subspace of dimension k of this larger vector space fq to the k. There is another equivalent definition that you might have also seen, and have definitely seen parity check matrix yesterday when Monica was explaining the syndrome decoding problem. So the parity check matrix is this like a matrix H of size n minus k times n. And then like it's defined so that basically once it's multiplied with the transpose of the generator matrix, it gives a zero vector. So this is also a zero. This is a zero vector, so I will use it also to denote the zero matrix as well as a zero scalar, so zero is zero everywhere. Okay, and using this parity check matrix, we can also define the linear code equivalently to the previous definition, so that basically all code words that are in our code are actually the vectors that are in the kernel of this parity check matrix. And yeah, maybe you have seen this definition already before. So this was the encoding part that, as I mentioned, like it was very easy. You just do some like matrix vector multiplications, everything is polynomial. So this is the easy part. The question then is, how do we correct the error of this message? And so let's start with what the error is and how do we model it. So it's basically another point in this vector space fq to the n. We denote it by e. And what we know that in the process, this error, like in my case, I will model it as additive error. So we just add bit by bit, like all the all the indices of this error, we will add to the indices of like the code words. So this plus here basically denotes the position-wise addition of the like error in the code word. And since we are in the space fq to the in the like finite field fq, that means it's basically a modular addition. So I'm not using XOR here, just not to confuse that it's not always in the binary field. So it can be any finite field. So we have now the noisy code word c tilde, and as we seen earlier, our goal is actually to start from this noisy code word c tilde that is in fq to the n, and obtain original code word that is in C. Okay? And to do so, we can have the approach that Monica described yesterday. So basically, so what is the setting now? So we have like some random point in this vector space fq to the n, and we want to find the closest code word point. So this like code is basically a linear subspace. So we know that there will be some points in this huge vector space fq to the n that are not in the code, and we want to find the closest one. And then we come to the point where we actually need to define what does that mean to be the closest one. And in the case, or in the like coding theory setting, what do we mean by that is that we are actually modeling the distance between the 2 points in the vector space using the so-called Hamming distance. And I guess you have also seen this before. So basically the Hamming distance between two vectors c and c tilde tells you what is the number of positions in which the two vectors differ. And from this distance function or metric, we can also derive the notion of the Hamming weight of a certain vector, which is basically the distance between this vector and the origin of the space, or zero. And equivalently, you can also say that like the Hamming weight counts the number of non-zero positions in a certain vector. Okay? So once we have like this definition of what does that mean to be close, we can also define the decoding methods. And the first one is the one that I have already mentioned, so the so-called minimum distance decoding. So we are given the noisy code word c tilde, and we are asked to find the code word c at the smallest Hamming distance. Okay, very natural. One slightly less natural definition is the one of the syndrome decoding. So it goes as follows. We calculate the syndrome S, that is a vector in the space fq to the n minus k. And we define it basically as the matrix vector multiplication between the parity check matrix and c tilde. And yeah, what you can see here is that, yeah, I just wrote down like what is the c tilde. It's basically c plus the error term. And since we know that all the code words are basically in the kernel of the parity check matrix, this part will cancel out. And what remains is just this part that is basically the parity check matrix times the error vector term. Okay, and now again we are asked to find the error E that satisfies this, and also it has the smallest possible Hamming weight that is non-zero. Okay, so this is the setting. Yeah, and this is everything that I wanted to tell you about the preliminaries on the coding theory. So do you have any questions on anything or something that is not clear? So maybe I can also mention some notation conventions that I'm using here, but you probably even figure it out yourself. So the small bold letter is vector. The capital bold letter is a matrix, and non-bold small letters are scalars. That's basically it. And yeah, so here also this is a vector matrix multiplication, actually matrix vector multiplication. So I just don't denote it at all. Okay, yeah.
You were talking about linear codes. So it seems to imply that there's also non-linear codes. Are they also used for crypto or otherwise?
So I'm not aware that they were used in crypto, but they definitely exist in the coding theory. So that's what I can answer. I have not worked on these, but for sure I know that they exist. And sometimes the theory behind them is quite similar. But I think that in the case where you have nonlinear spaces, it would be slightly harder to actually implement it on computer. And yes, in some sense, at least in the digital computer. So I think that for sure there existed some nonlinear codes, especially in the era before the digital. And so when you still had the analogous domain. But yeah, so in the code-based cryptography in the setting, I'm not aware of using nonlinear codes. Thank you. So let's now move on to the computer science setting, where we're actually discussing the problems, their hardness, and why these problems are at all relevant to us. So the decoding problems I'm going to talk about today are computational problems that are derived from minimum distance decoding and the syndrome decoding. And I will just give you now the definition of these two types of the problems, but through the lecture, you will see different variations. So when I say there is two types of problems we are interested in the most, it's just as two classes of the problems, but within these classes, you have many variations and many possible different problems. Okay, and I would start with something that I call the code word finding problem. You might have also seen some different names, just decoding problem, or in the literature, there is different ways to call the same problem. So what we have here is that we take, so it's called code word finding problem. We take as an input a generator matrix G of a linear code C. And we also get a noisy code word C tilde and a weight W that is some integer value smaller or not greater than N. Okay, so that's our input. And our goal is to find a code word C that belongs to the code. Such that the distance between C and C tilde is not greater than W. Okay, so now can someone tell me, do you notice some difference in comparison to the technique that I explained? So minimum distance decoding and the problem I'm describing here. And there is a difference, that's why I'm asking. Can someone tell what would be the difference? And I will not let you go before you answer, because that means that you're awakened. And also I can, but to help you, I can go back to the definition. So this is the minimum distance decoding definition. So given a noisy code word, we are asked to find a code word that is at the smallest Hamming distance. And here, we are asked to find the code word that is a distance closer, that is a distance smaller or equal to W. Yeah.
Previously, you were trying to find a minimum.
Yeah.
And now just some distance.
Yeah. So exactly. So the biggest difference is that now we already gave the parameter W that tell us like what is the bound. And do you have any idea why we would introduce this type of like modification? I mean, ideally, we would really like to find the closest possible code word. What is the issue with that?
It's too hard.
It's too hard. So basically for our purposes, it would be just very hard even to verify what is the closest code word. So yeah, the problem would be like, for our purposes, not useful. So that's the reason why we introduced this additional parameter, W, that basically tells us in which region we are searching, okay? And this parameter W, as Monica mentioned already yesterday, is a very crucial point here. Because like if you're just asked to find a code word that is in the code, can you advise me a very easy algorithm that can actually do that in polynomial time? You have seen it yesterday. So without this like additional constraint on the weight, what would be the way to find the code word, given the parity check matrix and the C tilde? Yes, so very simple, like high school, like math. Just perform Gaussian elimination, polynomial time. It would be very easy to do it. So this problem would not be hard at all. And so, but on the other hand, like as soon as you fix this parameter, this problem can become hard. It's not necessarily true always. So what does this parameter controls is actually the number of possible solutions. So if you completely like forget about this like constraint on the weight, you will have many solutions, and that's why. So you will have underdetermined system of equations. So there will be many possible solutions. The problems becomes easy. As soon as you fix this parameter, this problem might potentially become hard. And in fact, there is a way to fix this weight, so this problem becomes very hard because it gives you. So there is only one solution to your problem, which means that it's very hard to be found. Okay. And to actually analyze this like problem also from more theoretical viewpoint, like complexity classes and how hard is it in like a very theoretical sense. So we also can define the decisional version of this problem, where you basically have exactly the same input, and your goal is now not to find these like closest code word, but or actually the code word at the distance not greater than W, but you just need to decide if such a code word exists. Okay. Okay, and yeah, I will comment on the hardness of this problem once I also introduce the syndrome decoding. Okay, so the syndrome decoding problem corresponds to the syndrome decoding method. So again, we are given a parity check matrix H, a syndrome S, and the weight W that is not greater than N. And we are asked to find the error that is in FQ to the N such that it satisfies the syndrome equation, and also like the weight constraint that is given by W. Okay. And similarly, as for the code word finding problem, it's very easy to find the decisional version of this problem, where you just ask if such an error vector exists. Okay. So now the question is like, how hard are these problems? And yeah, in fact, people worked on that, and they proved that these problems are NP complete. And in particular, they reduced to the three-dimensional matching problem that is like a well-known like NP complete problem. I mean, for me, it became known when I started reading about like the syndrome decoding and like this type of literature. But apparently, it's like well-established like a NP complete problem. And yeah, so once I was giving a talk, so someone told me that this had not been the first like place where they actually showed it. So, but you would probably need to ask like some French research community, like because they are very like they're trying to be very fair, and they're always explore like they go always to the first reference possible. So yeah, maybe I'm not completely right that this was the first place where this was proven, but this is like somehow very established literature for this problem. Okay. So, but yeah, the NP completeness, what does it tell us? So once the problem is NP complete, what we know about it is that actually, if it's it's very hard to find solutions to this problem, right? So we assume that we will have like some exponential like running time algorithms. Nevertheless, it's very easy to verify. And that's why we come back to our definition of the problem, where we fix this like weight W. So in this case, so if this weight W is fixed, the checking, like if something is of weight W and if it's in the syndrome or if it's like a code word, is very easy. Nevertheless, finding it's actually a hard part. But it still does not tell us enough about this problem. So the NP completeness is basically telling something about the worst case instances of the problem, but it does not tell anything about the average case instances. And for cryptographic purposes, it's actually what is relevant to us. So how our systems behave on average and what we can expect from them, not only for the worst case instances. And for that, it's actually a lot more important that we have some proper cryptanalysis of this type of the problems, and that we show that there is no very efficient, neither classical or quantum algorithms that can solve this type of problems. So in particular, what we know so for the conveniently chosen parameters, and I will explain what does that mean to have conveniently chosen parameters. So the problems are computationally hard for all known classical and quantum algorithms, or equivalently for the best known. And so what we mean by conveniently chosen parameters, so we choose them to have, as I mentioned, so this it's possible to create the pair of the parameters, to choose the parameters such that there is only one solution to a problem, in which case you say that you're in the unique decoding regime. And in that case, the problem becomes very hard. So I put the star here. So typically, it's not necessarily always true that you are choosing this problem in the unique decoding regime. It can happen that you have some different regimes and that your problem is still hard enough. But yeah, so for the purpose of the talk today, I'm just going to talk about the unique decoding regime. And what we know about this regime is that the best classical and the best quantum algorithms run in exponential time in the input size. So in this case, it's n. So yeah, basically n is larger than k and w. So yeah, we observe everything in relation to n. And as such, these type of problems are considered to be very good basis for the code-based primitives, and they're also considered to be post-quantum. Okay. Yeah. Yeah, I feel that people are still a bit asleep, but okay. Yeah, and I would like also to have a brief remark on the relation between these problems in the code-based domain and in the lattice-based domain, the things that you have seen 2 days ago in Subha's and Leonard's talk. So yeah, I think that maybe the definition was not exactly the same, but the spirit was there. So the problem is called, in the lattice-based literature, is called the bounded distance decoding, where you are given a lattice basis. Yeah, you can basically see it as an equivalent of the generator matrix. You have some parameters m and n. I will comment on them slightly later. A target vector t, which is basically your noisy code word, and a norm bound beta. So and then your goal is to find a lattice vector that is, yeah. So this is a notation for lattice that is generated by this basis, such that the target vector is not too far from your lattice. So in particular, is closer than beta distance. And in this case, what we have is that we are not observing anymore the problem in the Hamming space, but in the Euclidean space, or the L2 norm. For that one, I don't think you need the definition. Yeah, okay. So, and there is another problem that can actually be seen as equivalent to the syndrome decoding problem in a way. So it's called short integer solution problem, where you're given a matrix A of in some, yeah. So with with integer entries and a norm bound B again, and you're asked to find a non-zero vector that is in this z to the n, such that it's basically in the kernel of this matrix modulo Q, and that it's not that its norm is not greater than beta. So this can be seen very easily that there is a lot of things that are corresponding between the two types of the problems. Nevertheless, so yeah, despite of these similarities, so we see that this problem have a lot of analogies and equivalences, and apart from from this very intuitive way to see that, what we can also see in the cryptanalysis of this problem, that when you use similar techniques, you get similar improvements for solving these problems. It does not mean that if you use the same techniques, you will have exactly the same numbers in the lattice and code-based domain. That would be a bit also weird to see, but you will have probably the same kind of improvements. So it's a fair question to ask, are these problems really different, or they're actually the same problems in the same parameter regimes? And this is a very open research question. And so this is the reason why people believe they're not exactly the same, but like very similar and very close problems. But there is also the reasons to believe that there is actually some inherent difference. So first thing, these problems are defined over different matrices. So Hamming space and Euclidean space are not the only like metrics that can, or Hamming and Euclidean are not the only metrics that can be observed in these two spaces, but in general, so the Euclidean is the default one for lattice-based crypto, the Hamming is the default one for the code-based crypto, and you can already see that there is like something different going on in that case. The other thing is that the best possible attacks in the lattice-based setting and the best possible attacks in the code-based setting are not the same. So we have like some like similarities between the techniques, but those are not the same techniques. So there is some reason to believe that there might be some inherent differences why why certain attacks work better in one domain than the other. And then we come again to this research question: is it the same problem? And it becomes increasingly important in in the situations like, you know, I don't know if you were aware of this like a lattice-based apocalypse from the last year. So when there was like a paper that was like, yeah, it seemed that it's actually like is able to like break the lattice-based problems like in like very like fundamental way. Not necessarily like the implication to the like standardized schemes by NIST was not completely clear, but still it shook like it was like a very strong shock for the field. Yeah. Yeah, exactly. So this was a quantum paper. Yeah, that's an important thing to mention. But yeah, so it was like the quantum paper that was claiming that it destroys basically all the lattice-based cryptography. And at that point, people start wondering, so what does that mean? So do we have like really a valid like alternative? So is it really the codes that are so different or not? And then like at that point, people start saying that, yeah, maybe the codes are not the same. But like if you ask them in any other point in time, people are like, yeah, it's exactly the same thing. So you don't need to think about that more. But in fact, we should think a bit more about that. And you can even go farther with this like analogies. So multivariate also has some similarities. And in particular, it also shares certain type of attacks, or at least attack techniques. So yeah, the question is like, how big is the variety of the problems that we are offering? So one, yeah, like quite different area of like research and like post-quantum problems is like what did I hear the talk about yesterday? So I believe that, yeah, you talked about isogenies. So isogenies are quite different, like flavor. It has quite different flavor of the problem. So they are truly like very alternative, but for the rest, we should really be careful about these like connections and making very quick conclusions how close or far they are. Okay, so after this intermezzo, yeah, I can move on. Okay, some questions? No? Okay, so now we are going into quite technical part. So the question now is, do you need a break? Like maybe 5 minutes or something, because like so there is like two more like fairly technical parts, the part on the code-based PKEs and the part on the digital signatures, and then there is like a very light conclusion. But if you need a break, I think that's now it's a good time. So maybe 5 minutes or something like that. Yeah. Okay. So yeah, if you're ready, we can continue. So as I said, I would like to start with a slightly more technical part now, which is on the code-based public key encryption schemes and key encapsulation mechanisms. And as you already heard, like in the last 2 days, so probably you have already known that before, but so in the so public key encryption and digital signatures are like the baseline, are like a very fundamental primitives in cryptography in general. And these are the first things that we are also trying to migrate to the post-quantum. And I would like to start now with the one example of the public key encryption schemes. And in this case, it's like, so it's a setting in which we basically have a public key and a secret key. And the goal of the public key encryption is to securely transmit the data over insecure channel. So now we are in a slightly different setting from the coding theory setting where we actually have malicious parties. So someone is attacking us potentially, and we want to defend our data and not to provide any leakage to these like eavesdroppers or like even more active adversaries. And the key encapsulation mechanisms is something like very related to it, and it belongs to this like pre-quantum era like of hybrid that Bart mentioned. So where you used this like key encapsulation mechanism to actually establish the secret key between the two parties that potentially don't even know each other. And in both these cases, the basic principle is the following. So you have a public key that encrypts the data, and you have the secret key that is actually used to decrypt it. So on the like prover side or like the sender side, you have the public key, and this public key can be known to many people. And on the receiver side, you have the secret key. A receiver can also know the public key and also sees all the communication, but it's the only person that actually has a secret key. Okay. So in the case of the code-based public key encryption and CAMs, the security relies on the computational hardness of the decoding problems. So the ones that I introduced, but also variations of these problems. And those are considered to be one of the most prominent candidates for post-quantum. So like the reason why I'm mentioning this one, like the example that I'm giving is because it was like decided to be standardized by NIST, but there's also others that are like part of some other standardization processes or some other schemes that were used like by certain limited communities. So in general, they're considered to be quite like, that it has quite high potential for post-quantum security. Okay. So the scheme I'm going to introduce is called the HQC, which comes from the Hamming quasi-cyclic. And it's a public key encryption scheme that is selected for that is selected to be standardized by NIST like a couple of months ago. So it's still in the process of being implemented. And the security of the scheme is based on the hardness of the decoding problems over quasi-cyclic moderate density parity check codes. And like, yeah, I will explain this like a huge term, like what does that mean? But the reason why like we are observing now a variation of the syndrome decoding problem is that basically this type of the QC MDPC codes have like quite compact structure. So it's easy to describe the codes, like you can efficiently describe them and send them or like share them between like parties. And yeah, so because of that, they are leading to like faster like encryption and decryption, and also smaller like ciphertext and signature. So the ciphertext and public and secret key. Okay, but let's start with the definition that is necessary for understanding like what like quasi-cyclic mean. So we start with the definition of a circulant matrix. We have the vector H that basically is some vector in the space F to the n. And we then define the circulant matrix that is like generated by H as follows. So yeah, this like operator rotation maybe becomes clear when you see how the matrix looks like. So in the first column, you have like basically the vector itself. So from H0 to Hn-1. And then like for the next column, you just put the last position to the first one, and then you continue rotating till you reach the full like permutation. And that's the parity check matrix that you obtain that way, and it's of size n times n. Okay, and this can be used to obtain the so-called systematic quasi-cyclic code that is given by the parity check matrix described here. So it contains like on the diagonal, it contains different small identity matrices. So you can imagine them as blocks of identity matrices that are put on the diagonal. And at the end of each of like this block of matrices, you have like this circulant matrix that is generated by vectors H0, H1, and Hs-2. So it creates a new, like a huge code that is like of length Sn and of the dimension n. And yeah, so sorry for the notation is slightly different here, but this was the best way I found to actually present the scheme. So Sn here is used to be n for the previous codes, and n here is basically what is used to be k in the previous codes. Okay, so this is parity check matrix we are going to observe, and in the HQC case, we will basically have just this first part, so one identity matrix and one like quasi-cyclic, or sorry, one circulant matrix here. Okay. And now we come to the scheme itself. And yeah, I'm also very happy that I don't need to introduce the definition, like what does that mean to have an encryption scheme. So I will try to represent this as like kind of a comic. And I still hope that you will be able to have the big picture. But yeah, probably you remember from like the previous talks that like every encryption scheme starts with key generation. So you need to describe the algorithm that will enable you to generate these two public and a secret key. So in the case of the HQC, it starts by sampling some generator matrix of size k times n, as well as this vector h that is going to be used for creating the large parity check matrix. And it also samples like two vectors, x and y, from the spheres of radius w in the vector space f to the n. So both of them are like from these spheres, or equivalently, those two vectors are basically vectors of weight w. So that's like, yeah, I'm just using this like notation of a sphere. I hope it's not super confusing. So yeah, we sample that. And then we create the parity check matrix H as this like a quasi-cyclic circulant matrix. And then we calculate what is the syndrome that corresponds to H and X and Y, where this like comma basically denotes the concatenation of X and Y. And what we end up with, because like this part is like identity, so we end up with X in this like first part and H times Y in the second part, where this like operator here basically means that you are just multiplying like pairwise like positions of these vectors. So yeah, so if you have H times Y, it's basically H0 like Y0, and you just continue. Okay, so yeah, this is like, I will use this notation because it's more convenient than have transposers everywhere. Okay. And what you get this way is basically you obtain the public key, that is this like the H, the vector H that is used for generating the parity check matrix, the syndrome. And the secret part is this like X and Y. So this is the thing that we should not leak in any like in any of the algorithms that follow. So this is what we need to keep secret. This part is like known to everyone. Okay. So what is now like the setting of the public key encryption? So sender starts with like, yeah, deciding on which message like she wants to send and uses the public key. The receiver also knows the public key, but the secret key is the crucial part that only receiver knows. So the sender will then try to encrypt the message using this public key. And in the case of the HQC, it's done as follows. So it samples like an error vector that is from another sphere of radius WE. And this is also a parameter that is chosen by design. So all this like, in this case, WE or like these WR are chosen by designers of the scheme. So it's something that is optimized. And apart from this like error vector, it also samples two vectors R1 and R2 that are coming from the sphere of radius WR. Okay. And for all of this, like to understand the intuition behind the schemes, it's like very non-trivial to explain it. It's also probably not super trivial to understand it. But like if you really want to go into like, yeah, like intuition and a full understanding of the scheme, I would advise you to actually read the documentation. So these documentations for the NIST submissions are actually quite good. So they explain a lot of things. It's not like just a very technical thing without any definitions or anything. Okay. So then what happens, like we compute the vector U, that is basically kind of another syndrome over R1 and R2. So you multiply the parity check matrix with this concatenation of R1 and R2. And what you obtain is this vector U, given here. And you also calculate something that is called, like that is denoted by V, which is basically encoded message using this parity like the generator matrix G, plus some error term. Okay, and what we send as a ciphertext in the end is basically those two values, so U and V. Okay. So this is a ciphertext that is sent from the sender to the receiver. And what the receiver now wants to do is actually to recover the original message from the ciphertext and the secret key. And the way it is done, it's actually very simple. So you just like subtract from this V, you subtract the U times Y, where Y was like this part of the secret key that you know from before. So you cannot like calculate this if you don't know the secrets. So you can guess why, but probably you will not be able to decode properly. And then, yeah, so decryption basically comes down to decoding like this term. Okay. And when I say decoding, I refer to algorithm that is chosen to be used to decode the code that is generated by generator matrix G. So we will try to first create a code that can have like enough of error correcting capability, but we will then also decide on which particular decoder we want to use, because like for different codes you don't have like just one technique possible to perform the decoding. You have many. Okay. Yeah, there was a question, maybe you have not seen it, like if people are sleeping. So yeah, I wanted to ask like, what was the first thing that actually you expect from the scheme like this? So you encoded something, you send it, and you want to decode it. What do you expect from your scheme to guarantee? Like a minimal requirement. Sorry? Yeah, exactly. So you want to receive the original message. So that's the basic idea. So what you basically claim that your scheme does always is that it's correct. So it's correctly decodes the original message. And in this setting, so you can write down like what is V, what is U. And you can see that you basically come down to the expression that is written here. So you have this like encoding, like encoded message M times G. So it's like some vector in the space like F2 to the n. And you have something that is basically an error term. And what like ideally you want to do is basically correct this error term. In this case, it would be very easy to recover the message. And this is like where the correctness of the scheme comes to basically decoding of or error correcting of this part. So in order to claim that your scheme is actually properly decrypting, you need to claim that your decoder is capable of correcting like any like number of errors that can be generated by this kind of a term. Okay? Yeah.
You can finish the sentence first.
Yeah, I finished the sentence. Please go ahead.
So this is eerily similar to LVE.
Yeah, it is.
So my question is kind of, if we consider this error term, and during the sampling process, we set the weight to something much lower than the decoder can decode.
Yeah.
Then technically this seems to be additively homomorphic.
Yeah. Okay, yeah.
Because then we could just add ciphertext and the error weight is then bounded by something we can still decode.
Yeah, but like in this setting, you're assuming that you're sampling error from a certain distribution, right?
No, just like with a lower weight.
Okay. Okay, so go ahead. And
no, the question is like, is this valid? Has anyone explored this?
I'm not. So what would you try to explore is actually that you can like perform this kind of decoding in the like a homomorphic way in a sense, or?
It's more like to say that. Yeah, exactly, because that's kind of induced then that the scheme is additively homomorphic.
Yeah.
And the next question would be, can you build something fully homomorphic?
Ah, okay. So, yeah, to be fair, I'm not sure. Yeah. I mean, I never thought about that. Especially, I mean, of course, you can observe this type of problems as like, more like LPN samples, like in the coding setting. Yeah, but I'm not sure if it can be seen as a fully homomorphic. Okay, so maybe I should think about it. We can also talk afterwards. But yeah, that's a valid point. Yeah. Okay, thank you. Yeah, someone is awake. That's good. So yeah, but let us assume that we are just trying to correct this error term. As I said, like to claim that your like scheme can correctly decrypt, you want this part to be like that we are able to get rid of this part, and which means that basically our decoder needs to be capable of correcting a certain number of errors. But what would happen if it's like if fails from time to time? So do you think that like this scheme is completely useless in that case? Well, not quite. So like in what we had like in most of these proposals, so what the like designers of the scheme were trying to achieve is that actually that the number of errors that this decoder like have is like not too high. So the coding failure rate can be non-zero. So you can have like some problems when you are decoding certain parts, but you just need to bound this type of errors and that to say that like they don't happen too often. Oh. Yeah.
Do you have any criteria when it fails, like it has failed?
Yes, so this part can be easily checked. So you can just like, yeah, maybe re-encrypt afterwards. So it depends on the design of the scheme, but like most of the time there is like some. Yeah, exactly. So the way to actually mitigate this problem is that you re-encrypt afterwards and you just verify that what you got is exactly the same. And this is like a point where like this is actually the approach that most of the code-based schemes, at least those that I am aware of, are using. And one of the like major concerns for most of the schemes is actually properly design these decoders to guarantee you high enough like level of confidence that it's correct. Okay, and I will come to this like yeah, to this point later on when I also explain one more scheme. Okay. So another thing, like apart from like this correctness, that is like somehow like a very default thing, it was the security of the encryption itself. So the whole point of like encrypting something was actually that you're not leaking any information in your ciphertext. And yeah, so this is basically the security of the scheme is based on that. And in the case of the HQC, it's not very hard to show that basically the security of the scheme completely relies on the hardness of the decoding problem over QC MDPC code that is generated by this parity check matrix that is basically like, yeah, this is what we call the quasi-cyclic and moderate density parity check code. Okay, so that's what we refer to when we say that we are observing a problem over QC MDPC codes. And yeah, but very valid point would be to ask like, okay, so now we just sampled one vector that is of size n, of the length n. So how do we know that like nobody would be able to exploit this like circle structure? So you're basically, in some sense, you're reducing the amount of entropy in your parity check matrix in comparison to what would happen if you just like sampled purely randomly this parity check matrix. So how it comes that nobody is able to exploit this? Well, that's a very open question. So nobody so far has managed to design any type of attacks that are able to exploit that. But it still does not mean that it will never happen. So we saw like already some examples of breaking different kind of structures. So even in the coding theory setting, not only in the multivariate settings. So we had like some breakthrough in the pseudo-random generation based on codes. So yeah, if you're really like crypto analytically inclined, I would encourage you to work on this type of things. Okay, so that would be everything about the PKE and CAM. So do you have any question regarding to that? Okay, so then the next hard part. So digital signatures, and like it's like, yeah, already some like one disclaimer. So now I'm going to say that I'm going to talk about the digital signature, but in fact I'm not going to talk about digital signature at all. I'm going to talk about the identification scheme from which you can build a digital signature. But digital signatures are actually considered to be the fundamental primitives, so we are actually aiming to achieve them, to obtain them. But most of the time it's actually very like technical to describe them, and like in particular the scheme I decided to use an example had a 4-page like a description in the documentation, so I think that we would not survive that one in the presentation, so I just decided to go the easy way. But let's start with what the digital signatures do actually. So we are again in the public key settings, so we have this asymmetry between the public key and the secret key. And in the case of digital signatures, what we want to achieve is to show that like a message that we are sending is sent like by a certain prover, like by a certain party. And then we also want to show that this message has not been modified. So these are the two goals we want to achieve. And the basic principle is actually to use the secret key to sign a message and the public key to verify a message. So in a sense, you can see that as a mirror process to what we had before. So now the secret key is only known to the one who is sending this message, and the public key is known to everyone else. Okay? Which kind of makes sense because then many people can actually check if a signature is valid. Okay, and as before, the security of the code-based digital signatures relies on the computational hardness of the decoding problems. I'm not aware of like any scheme that is actually like Monica mentioned yesterday, they're in multivariate, and also like in some other like places you can find the schemes that are not fully relying on the hardness of the problem, or some more ad hoc like designs. I'm not aware of these. Like from all the schemes that I know about, they always rely on the hardness of the problem. So, and the security is well understood. And again, so you have a lot of these schemes that are actually now considered to be standardized by different standardization processes, and NIST now has these like round 2 on the ongoing digital signature standardization. And the scheme that I'm going to describe today is actually part of this like round 2 process of standardization, and it's called CROSS, which comes from Codes and Restricted Objects Signature Scheme. Okay. And the scheme is based on the restricted syndrome decoding problem that I'm going to describe now. And before I do so, I would first like to start with the definition. What do you mean by restricted? So I think like the definition of restricted is quite particular to this like scheme design, because like the authors like decided to restrict the way it was very convenient for them. And to define it, I would start with the definition of what we mean by a restricted vector. So we take FQ to be like a finite field with Q elements. Q is here needs to be a prime number. And we let FQ star to basically denote its multiplicative group that corresponds to FQ. And we know that the order of this group is Z, which is like smaller or equal to Q. And Z is another prime value. And given that it's like, this is of a prime order, we can also define the generator G, which would be the group generator, which is just an element of this group. And using that G, we can actually generate all the elements in the group by just like multiplying them. Okay, so G to the I basically means like multiply this like G I times. And why this is convenient is basically you can very easily describe the whole group by just simply giving a generator and then the indices, so like from 1 to Z. So this description of the group is slightly more compact than if it was not chosen this way. Okay, and it will become very relevant once we decide to design a scheme in which we need to send the description of this group. Okay. And then we go to the restricted syndrome decoding problem, very slight variation from what we had before. So again, we have the parity check matrix as the input to the problem, a syndrome S. And here now, what is the difference? That we also define a set E that I introduced earlier. So it's basically a restricted set that we are going to use. And again, we fix some weight W. And the question now is, again, to find the error that satisfies the syndrome and like the weight constraint. But like the difference is that now the error needs to come from this restricted set. So it used to be like any error from F2 to the N, but now it needs to come like from this restricted set. And equivalently, we can also define the decisional version of the restricted syndrome decoding problem, where instead of like just finding E, we are deciding if such an E exists. Okay, what do we know about this type of problem? Well, the authors again showed that it's again NP complete. So like at least it's like intuitively it makes sense to try to use it for the cryptographic purposes. And it's also shown that that for conveniently chosen parameters, as before, it's probably in this case it means that it's like unique decoding regime. So the problem is computationally hard for best known decoding algorithms. Most of them I'm actually going to explain tomorrow in the talk on the cryptanalysis of the problem. But apart from that, it's also safe against algebraic attacks. And this is like slight modification, or slightly larger set of attacks that is normally analyzed. And the reason is that basically algebraic attacks that Monica described yesterday work quite well, like when you have like this queue that is larger than, that is quite large. So when you don't have like a binary finite fields anymore, but you're observing over some finite field of size q. In that case, algebraic attacks can bring you some benefits. Nevertheless, in this case, the authors actually show that it's like the algebraic attacks are not more efficient than the coding ones, and all of them are running in the exponential time in the input size. So the problem seems to be computationally hard enough for all our purposes. Yeah, and so the reason why they choose to use this type of a problem and restrict this set in which you can have the error is, as I mentioned earlier, so compactness of the description of the problem, and also, yeah, the instance of the syndrome decoding, but also the fact that you can perform some arithmetic operations like easier than you would do that if you were just observing everything in the space FQ, in the finite field FQ. So at least half of the arithmetic operations are performed over this smaller field FZ, and modular multiplications can actually be reduced to modular additions, which gives you like like benefit and like in the sense that you can perform your equations, like your calculations faster, and which gives you more efficient scheme. So that's the basic idea. Final thing that I need to also mention here as the intro part to the scheme is that, so in contrast to what you saw yesterday, I think that you had like a 3-pass protocol or a sigma protocol. The scheme presented here is a 5-pass. So yeah, it's an identification scheme in which you start with the prover that has a secret key. Then like the prover commits to 2 values C0 and C1 using this secret key. It sends it to the verifier. The verifier then samples a challenge from set of like challenges for the first challenge, sends back to the prover creates a response, then sends it back to the verifier, then the verifier creates a new challenge, response, and finally the prover needs to provide the last response, after which the verifier like decides if the prover managed to prove its identity. Okay, so the idea is that you have like some kind of interaction between the two, and then like the goal is that the prover convince verifier, if the prover is honest, prover managed to convince the verifier that it knows the secret key, and if the prover is malicious, that it's not possible to do so. Okay, that's the idea of the 5-pass protocol. And the cross-identification scheme that I'm going to describe falls into this category of 5-pass protocols. And afterwards, like why I decided to describe it is basically it leads to the digital signature, and the way you do it is actually quite generic. You use the Fiat-Shamir transformation to basically remove these like interactions, and that way you obtain the digital signature. And again, like as in all the encryption schemes you have seen, like all the like primitives that you have seen so far, like we start with the key generation. And in this case, the key generation is actually quite straightforward. So you start by sampling a parity check matrix H, like of size n minus k times n, a generator that will actually create your tiny group or like restricted set E. And you just need to be sure that like this generator actually creates a set of like a size Z. And you also sample the error vector that is in the subset of this E to the n. Okay. And then you calculate the syndrome based on the parity check matrix and the error vector that you sampled. And yeah, very intuitively, you decide to use like your error as a secret key and your parity check, the syndrome, and this like the set G, so the subset of the restricted set as like your public key. Okay, so and that's one of the reasons why I decided to use this scheme as an example. This is the most like straightforward possible way to actually use the syndrome decoding problem. You just like create the syndrome decoding instance, and then you just put it into public and the secret key. Okay. And now we are in the setting of the identification scheme. So the prover has the secret key, the verifier has the public key. And the prover starts by committing to certain values using the secret key. And in the case of cross, it goes as follows. So it samples 2 values, U prime and E prime, from the FQ to the N and G. it then calculates the value D that belongs also to the same set or the subset. And this, so this D needs to satisfy that D times E prime is equal to E. So which means that like the prover that commits to these things actually needs to know this value E to be able to calculate this thing. So basically needs to know the secret key. And then it also sets some value U and S prime that is basically another syndrome. I will not go into details what is the intuition behind this. But the bottom line is that after that, it calculates basically the commitment 0 and the commitment 1. And every time you're actually trying, so this is a pretty generic way to do that, like you hash some values. And the reason why you're hashing these values is, first thing, so the goal here is to commit to certain values. So you're not supposed to be able to change your answers based on your commitments or change your commitments later on during the interaction. So what does this hashes provide is actually that you're computationally binding to the values that you have sent. But what it also should provide is that these values that are here should be somehow protected in a way that they look random. So you don't really see this S prime and D and U prime and E prime in plane. They're you can see them as random values. This is a hiding property of the commitment scheme that is always desired. Okay, and once we commit, so the prover committed, it sends the C0 and C1 to the prover, to the verifier, sorry. Then the verifier issues the challenge. In this case, the challenge is sampled from FQ, from the finite field, so you have Q possible challenges. Sends back this challenge to the prover, and then prover calculates the first response. So the first response is I will not go into details how is it calculated, but you just simply add some values, multiply with the challenges. So in some sense, the challenge itself affects the response of the prover. And then it hashes this value again and sends it back to the verifier. So that's the first response. Then the verifier chooses the challenge from the set 0, 1. So basically, this part just corresponds to the fact that if a verifier wants to get the answer from the prover about the commitment form, or the first commitment or the second commitment, sends back to the prover, and then the prover, in the case B was equal to 0, that means the verifier actually wanted confirmation of the commitment 0. So the response will correspond to that commitment. So it will just send Y and D, where this value D could not have been calculated without the knowledge of the secret key, and also one of these two values cannot also be calculated without the knowledge of the secret key. So in the case the response was equal to 1, so the B was equal to 1. Basically, the prover provides the proof for the first commitment. Okay. And as simple as that. So it just sends back the response. And finally, the verifier takes all the context into account. So the public key, the commitments, the responses, the challenges, and just decides if the prover is the prover has managed to show its identity or not. Okay, so that's as simple as that. And what we normally desire from this type of the schemes is that they are complete. So we want to have a property that if the prover is honest and it's really the person it claims to be, then it should be possible for it to prove it. Ideally, we want that to be always possible for the prover. Nevertheless, in most of the schemes, we can still allow for some certain margin of error that sometimes it's even for the honest prover, it's not possible to actually prove in certain instances that the identity is not possible to be proven. Nevertheless, if it's a small enough fraction, we still consider it to be a valid scheme. And apart from the completeness, what we also desire is that for the malicious prover, it's actually not possible to prove their identity with overwhelmingly high probability. So that's basically, So in the first case, we have for someone that is honest, we want it to be able to show the identity. For someone that is dishonest, we don't want to allow them to cheat. And we call that the soundness property. And in the case of this scheme, it can be shown that the probability of cheating is given by these values, by these expressions. So Q over 2 times Q minus 1. And depending on the size of the queue, you can argue that this seems like as not good enough. So I mean, like imagine that like, for example, if Q is equal to 2, so you have like probability of cheating almost equal to 1/2. So it doesn't really sound ideal. Yeah, I mean, like if you have this type of like a like identification scheme, I don't think it would be considered very reliable. So what you can do in this case, first thing, you can choose Q properly. But the second thing is that you can repeat this protocol many times and only accept the proof of identity in the case when the prover was able to answer all the challenges correctly, when the prover managed to show its identity in all the possible runs of this like algorithm. So you imagine that you run this algorithm 10 times. So then the probability of like cheating in that case would be like this expression to the power of 10. That's the way how you can actually boost your how you can reduce your like cheating probability. Okay. And yeah, as far as we know, there is no known attack that can exploit this restricted structure to actually like increase this like cheating probability even more. Again, so it's like open research question. Problem is relatively new, so I encourage you to cryptanalyze it and try to show it's possible. Okay. Yeah, and the final property of this scheme that is also very important is zero knowledge property that basically tells you that apart from the like showing the identity of the prover or actually confirming the identity of the prover, it's not possible, you don't have any additional leakage of the information about the secret key in particular. And this type of the protocol can actually be transformed into like a zero knowledge digital signature using the fiat Shamir transform that, just basically removes all the interaction that you had. So you can imagine that your protocol was run multiple times to boost this soundness error, or actually to reduce this soundness error. And then in order to remove all the interactions from your protocol, you just want to remove challenges because this is the only thing that is done on the verifier side that needs to be like, this is the only part where verifier is actually active. So if you remove this part and generate your challenges using the hash function, then you remove the interactions and you basically obtain the digital signature that we started from. Okay. Technical part done. So now we have like a couple more minutes for the final remarks. Also like some more philosophical questions about where all this field should go. So I mentioned like so far like 2 examples of the scheme. Of the schemes, there is like a lot more than that. So these were like just illustrations. But so for all these schemes, there are some generic techniques to improve their like efficiency, and you have seen both of these techniques yesterday in the Monica's talk. So the first one is the MPC in the head. So you have like a prover that in its head has like many smaller people that are actually doing some computations. And in the case of the syndrome decoding problem, these people can actually calculate certain parts of the error vector. They can communicate among themselves and finally come to the solution. And this is a generic technique that can be used to actually improve the efficiency of the scheme if you assume that like you have like this paradigm that like so this approach like a MPC in the head that is used on the prover side. I will not go into more detail than that. So just, in the case of the cross, it was also used for the optimized version of the cross scheme. Apart from that, you also have Merkle trees that can be used when, for example, like in all the schemes I was presenting, like just to be like a very, for educative purposes, I decided not to present like any pseudo-random generation processes that were happening there. So everything that I sampled purely randomly. But in the practical like applications, most of the time you would use pseudo-random generation to obtain enough of randomness. And in this case, like Merkle trees come very handy. There is also like, the Merkle trees can also be used in like combination with the MPC in the head. And all of these techniques are used not only for the code-based schemes, but more generally. Okay. So there are some generic techniques. Apart from that, like something that is more, that is also an approach that is used in different like in different post-quantum scenarios, is that you are introducing a structure to your problem. So what this brings to you, it basically brings you some like more compact way of describing your problems. Like the communication is like, more efficient, and also like the computations are more efficient. Nevertheless, so the unstructured versions of the problem, in this case, unstructured codes, are already able to avoid any structural attacks. So it gives you less attack vectors. So they are like, in that sense, they are better. Nevertheless, so structured code in general are like, the quasi-cyclic restricted codes, but it's not the only families we know about. In general, they have smaller keys and ciphertext, and they might be like, some new future potential structural attacks that would be able to exploit their structure and break the schemes. Okay, and now I would, the state-of-the-art schemes. So I have mentioned like 2 of them, but most of them are basically trying to find the best trade-off between this, like the efficiency and the security that they can provide based on this like level of the structure they introduce. So, like a quick overview of the schemes that did not make it to the standardization, but they were very close to it. So one of them is like a very well-known, the classical McLeese. It's based on the random GOPA codes. You can already see the word GOPA here. It basically means that you didn't have like a purely random codes, but you already had certain kind of a structure. Nevertheless, this type of scheme, or like this type of the problem, like underlying problem in this scheme was cryptanalyzed for 50 years. So we were quite convinced it's like very good. But lately, there were like some new attacks that potentially might say something that it's not as secure as we thought. Still, it like at least in the code-based community, it was considered to be one of the foundational schemes from which many other ideas were developed. So the main drawback was like a huge public key size that was preventing it from being very widely used. That was one of the bigger drawbacks before we started having also some doubts about the security. Another scheme that is also based on the QC MDPC codes is so-called bike scheme. And of course, I needed to mention because it was also designed partially by the people from like the group I was working in Paris. So I need to mention bike everywhere I can. The security was also considered to be quite well understood, especially since NIST competition started. Many people were working on the cryptanalyzing this part, this scheme. So it's also considered to be like well understood, even though it's there for a shorter period than classical McLeese. So it's still, some work still needs to be done. The biggest drawback is the decoding failure rate that I mentioned earlier. So they never managed actually to put it low enough to be very convinced that the scheme is not failing too frequently. Okay. And finally, one scheme that is dear to me because I worked on it is the scheme that you probably have never heard about. It's called the Stern scheme. It's based on the work of Jacques Stern. And it's based on purely random codes, so no structure at all. So the security is is as well understood as the security of the decoding problems, or the syndrome decoding problem in this case. But its major drawback is basically overall inefficiency. It's inefficient from all the possible aspects. Nevertheless, it is used as a starting point for one scheme that actually made it to the finals, and now I think it's also in the not the finals, by the second round of the NIST competition. It's the syndrome decoding in the head. So it's basically based on this Stern scheme, and then used MPC in the head technique to actually improve its efficiency. Okay, and the final thing that could be the direction for farther can be direction for future steps on working on the code-based schemes would be to try to target a bit more certain applications, not make the overall generic schemes that work for everything. So yesterday we also saw the examples of the stateful hash-based schemes that are used for particular purposes. So it would be also possible to use this approach here. But then we come back to this, the talk of the first day about this zoo of different possible algorithms that we can have, and then how we are going to end up communicating if we have so many different possible schemes. So yeah, finding the best trade-off between the two is, I guess, is what we are trying to do now. So the area is very active in trying to reach the best possible solution. And finally, why would we use code-based crypto and why we would not use it? So the first thing, it gives you a quite high level of confidence that these problems are very reliable. So they are analyzed from both coding theory perspective and code-based perspective. So in the cryptographic community, so in general, so we think that we know quite well how they would behave. And yeah, as I mentioned, a long history of cryptanalysis in the crypto field. But in general, so they are less efficient than some other alternatives. In particular, lattice-based alternatives most of the time are significantly more efficient. So we need to work hard on this aspect of making these schemes more applicable if we want to actually ever end up using them in a real life. Okay. So yeah, that was it from me for today. Thank you for bearing with me.